Hello, everybody. This is Mrs. Wild from WCA Physics B. We are looking at Unit 3, Lesson 4 on electric fields. And it's not as long as the last lesson, but I think it's a bit more tricky. So let's go through the details. So we have Coulomb's law, electric field, and field line as our first vocab words. And it's kind of discussing what an electric field is. Definition it's giving is the region around positive and negative charges where force is felt by a charge is an electric field. So each charge is kind of generating its own little electric field, and the strength of that charge is really a big part in determining the strength of the field itself, right? When we look at fields around charges, they are in different directions. So around a positive charge, excuse me, the field lines will point outwards from that charge. And around a negative charge, the field lines will point inwards towards the negative. So remember, outwards from positive and inwards from negative. So then we look at how do we determine how strong the field is? And as I mentioned before, it really is highly dependent upon the charge itself, like the strength of the charge. So the stronger the charge is, the greater the electric field strength is. So we can also determine like how strong that is based on a test charge that we put within the field itself. So if we have like a positive charge here, and again, field lines are pointing away, right? We have a charge that we put, my pictures are terrible, but we have a test charge that we place someplace in this field, and the test charge is always going to be positive. That's usually how kind of the standard is. So because it's positive here, it's going to be repelled from the positive charge that's creating the fields. This is our field generating charge here. And this test charge is going to be repelled away from it, right? And how strong this guy is determines how much force is pushing on our little test charge. So let's see here. They have an example, and it says, you can determine the force. It gives you the strength of the electric field as 250 volts per meter, which really I think it doesn't mean a lot to you at this point, but I'm trying to make it mean something before you leave or finish watching the video. You can determine the strength of the field. So I feel like this kind of comes backwards, but the strength of the field, like how do we get that? You're going to take Coulomb's constant times the charged particle that's generating the field divided by r squared, which is like how far apart is this test charge from the generating charge, right? So again, I'm gonna try my picture to be a little bit nicer here. But if I have my test charge or my generating charge here, right? And it's generating this. Sorry, I'm just really bad at drawing these, but I'm gonna do my best here. Try to make them more equal distance apart. Okay. And again, I said our test charge is positive. So it's gonna be pushed away. Well, if it's a couple things can affect how strong this field is, and therefore how much force is being used to push it, right? And the things that determine like how strong this field is how close you are to it and how strong the charge is in the center. So it'll push you away, and the closer you are is gonna push you harder. So if I'm like right here, you're closer to it, so you can feel it more, so it's gonna push you harder. If you're way out here, it's not pushing quite as hard, right? So r squared is greater because there's a larger distance separating the charge from the test charge. This is r, and that's bigger here, and this is r, and that's smaller. So if this number down here is smaller, then your electrical field strength is going to be smaller. So the field is stronger closer to the charge. Does that make sense? Field is weaker farther away from the charge. I think that kind of makes sense. It's like gravity, right? Gravity is stronger when you're closer to the Earth, and it's weaker when you get further away from the Earth. So it has a lot of parallels to gravity. All right, so and that gives you some math to solve. And I know I'm not going through the math, I'm going through the concepts, but the math is really plug and play here. Easy to do, but the concepts are a bit tricky. So we're gonna go ahead. We've got some more key terms: electric field, electric potential, equipotential lines, gravitational field, and voltage. And this is where I get kind of tricked up because I felt like the next 2 pages, they didn't really do a very complete job of explaining what I already knew, and it was messing me up a little bit. So they're kind of using the gravitational field as analogous to an electric field, which makes sense. If you're on Earth, again, as I mentioned before, if your Earth has a gravitational field around it and it's pointing towards the Earth, so it's actually kind of the opposite as a positive field, but it's like the same as a negative field that we've been experiencing. The field lines are closer together, so the closer you are to the Earth, the stronger gravity pulls on you. It has more of a force than if you're way up here, right? So that's kind of an analogy using the Earth's gravitational field as very similar. Remember, we looked at the universal law of gravitation and Coulomb's law, and they look a lot alike. So the similarities didn't really stop there. The other thing to look at is potential energy, electrical potential, and what we call voltage. And that's the next 2 slides here. So in the example with gravity, right? Remember our formula, mgh. So basically the big determining factors on, and remember that's, by the way, potential energy, right? So that's gravitational potential energy. I'm just going to write it like this. So we remember it's due to gravity. So the 2 major things affecting how much potential energy an object has is how massive it is and how high it is. So this guy way up here, if it's the same size, same mass as this one down here, right? The one that I circled in pink has more gravitational potential energy. Basically, what potential energy is, or energy in general, is the ability to do work, move a force over a distance, or you can kind of think of it in this case as cause damage, if you will. So if this guy fell down, it's going to make a bigger crater in the earth. It's going to do more work on the earth than this little guy here because it's falling farther. So therefore, by the time it reaches the earth, it's going to be traveling at a higher velocity, right? So we can say that the greater distance, the greater height, the greater amount of potential, gravitational potential energy something has in a gravitational field. Well, in an electric field, something is similar is true. Okay, so we have something called electrical potential. And electrical potential is also known as voltage. And voltage is defined as 1 joule per coulomb. When you think about that, that's the amount of energy it takes to per unit of charge. And when we look at gravity, we can think of the amount of energy per unit of mass, right? So with the picture that I just drew for you, the greater the distance between the Earth and the object, the more energy it took to move that charge or that object away from the Earth, right? So it has a greater gravitational potential. Electric potential is similar, but remember that we don't always have an attractive force. Sometimes it's repulsive. So it depends on the charge itself that's generating the field. So if we have positive, no, I'm going to do negative first because it's analogous. So if we have a charge that is negative and it is generating an electric field, that would be pointing towards right? You can see it's the same on all sides, but I'm just going to do the top part. If I have a test charge, remember those are always positive, and I move it further away. Now this test charge, because it is positive, it wants to be, I hate using words like wants and giving charges like human characteristics, but sometimes it helps, but it really wants to be close to the negative. It's attracted to the negative, so it wants to be there. So it takes me a lot of energy to move it up there. Also, if I were to stop holding it up there for some reason and just let it go, it's going to be attracted to the negative, and it has more distance to move, and therefore it can do more work. And therefore we know it has more potential energy. We don't say potential energy though, we say voltage. So the greater the distance between two opposite charges, that's the most important part here, the greater the voltage. When you look at like a battery, for example, no, I don't think this is necessarily true, but you have a positive and a negative end to the battery. We're separating those, the cathode, which is the positive end, from the anode, which is the negative end, and the greater the distance that separates them, not necessarily having a longer battery, but the greater those charges are separated internally, the greater the voltage, right? Now, what confused me, because I knew this already, was, oopsies, clear screen, okay, was down here, they're using a positive charge. So remember that in a positive charge, your field lines go outwards. So what that means is if I put a positive test charge in this field, it wants to be over here. It wants to be far away. So to do work on that, I have to push it and force it to go over here. So if the charge is closer, if my test charge is closer to that positive field generating charge, it has a position of greater potential energy because it naturally wants to be farther away. So this is where it actually has a greater potential energy. If I were to let go, this thing would fly away, right? So in the problem, it talks about how, sorry, sometimes these tools are a little complicated, how it has greater voltage towards, where does it say that? It says it here. Da, da, da. Since the strongest equipotential lines are closest to the charge, you lose voltage as you move away from the charge and gain voltage as you approach the charge. And that is true in this example where you have a positive charge. You are going to have the greatest voltage here, right? So let's say this is 200 volts here. I don't even know, I'm making numbers up, and 30 over here, because this has the greatest potential energy. But if the charge that had been generating the field was negative, it's the opposite. And that's the thing that was like messing with my head, and I wasn't, they didn't tell the whole picture, put it that way. Okay, so this is true for positive charges, and then you always, to get the difference, I suppose, is you take the final voltage minus the initial, which makes sense. It's just where that's going to be that differs. And then the last section of this lesson really just focuses on using that PhET simulation. And again, if you're skipping this stuff because you think I don't have time, but you're really struggling in physics, I would really suggest using it because these concepts are much easier to understand with visuals and interactive visuals specifically. So that is everything. If you have questions, let me know. Otherwise, I'll see you guys in the next one.